In the previous session, we defined Laplace transform, which is an operator that maps a function ft to a new domain, which is the frequency domain. And by definition, Laplace transform of ft is an improper integral from 0 to infinity of ft e to the power of minus st dt, and we call it capital F of s. So Laplace transform the function ft to a new function capital Fs, and in addition the domain is changed from time to frequency. We also calculated the Laplace transform of a few common functions, including a constant function a, which is a over s, and also Laplace transform of function e to the power of minus bt, which is 1 over s plus b. Another function that is commonly used in process dynamics is Heaviside function or a step function, which is often denoted by h of t, and it is defined as 0 for any negative value and 1 for any positive value. So the shape of this function is something like this. So for any negative value it is 0, and for any positive value it is 1. So if we use the definition of Laplace transform and take the Laplace transform of Heaviside function, it will be integral from 0 to infinity of ht times e to the power of minus st dt. Because this integral is only concerned with positive values of t, then we can say that at positive values of t, the Heaviside function is 1, and in fact we are dealing with a constant function of 1, and we've already calculated the Laplace transform of constant function a, which is a over s. So in this case the answer will be 1 over s. So the Laplace transform of a step function or Heaviside function is 1 over s. In addition to these three functions, there are other functions that we may need to take their Laplace transform. But for now, I will continue with this topic, and I try to get to the application of Laplace transform. And maybe when I show you a simple example of how we use Laplace transform to solve a linear ODE, then we can come back to this topic and try to drive the Laplace transform of more functions. Alternatively, I will post a table that has a list of maybe 20 to 30 functions and their Laplace transform, and you can just refer to that table and use it as a reference. Another important topic that we need to know in the context of Laplace transform is the inverse of Laplace transform. And its notation is the same fancy L to the minus 1. In order to understand how it works, I give you an analogy. So let's say we take the derivative of function t cubed. So it will be 3 times t squared. And now if we take the antiderivative or integral of the answer, which is 3t squared dt, we get exactly the original function. So that's why we call integral the inverse of derivative, or integral is antiderivative. The relationship between Laplace transform and inverse Laplace transform is exactly the same. So they are the inverse of each other. In other words, if I go back and, for example, for case number 1, take the inverse Laplace transform of the answer, which is a over s, the result will be the original function a. And if I do this for the second case, the inverse Laplace transform of 1 over s plus b gives me e to the power of minus bt. And same thing in here. And finally, another important topic that we need to know in the context of Laplace transform and inverse Laplace transform is that these two operators are linear operators. So Laplace transform and inverse Laplace transform are linear operators. And it means that they satisfy the principle of superposition. So in simple words, if I take the Laplace transform of an expression like a times ft plus b times gt, first of all, I can write this as the sum of Laplace transform of each term separately and secondly, these two multiplicative factors or coefficients, since they are constant, I can factor them out. So I can write this even in a simpler form of a times Laplace transform of ft plus b times Laplace transform of gt. And this property will be very useful when we get to use Laplace transform as a tool to solve linear ordinary equations. And finally, before I can use Laplace transform to solve any ODE, I have to define the Laplace transform of a derivative. So our fourth Laplace transform calculation will be the Laplace transform of derivative of a function with respect to time. And by definition, this is the improper integral of df over dt, or in short we can call it f prime, e to the power of minus st dt. But before I can continue driving the Laplace transform of the derivative of function f, I have to give you a refresher about integration by parts, because this is the method that we use to solve this integral. And if you remember, integration by parts is just an outcome of the product rules. For example, if we have the derivative of multiplication of two functions u and v, it is equal to the derivative of the first function u prime times the second function v plus the first function u times the derivative of the second function v prime. And now if I take the antiderivative of the two sides, the left side will be u times v and the right side will be integral of u prime v dt plus the integral of u v prime dt. And if I just rearrange this equation, I will obtain that integral of u prime v dt is equal to u times v minus the integral of u v prime dt. And this is a very useful relation which is called integration by parts. And I will just use it in here to calculate the Laplace transform of f prime. So in the same way, if I assume that f prime is u prime and e to the power of minus st is v, so let me just write them in here that u prime is f prime and v is e to the power of minus st. So if u prime is f prime, then u is equal to f, and if v is e to the power of minus st, v prime is minus s e to the power of minus st. Now what I do is I just copy this whole expression from here, and maybe I just move it down below. And I use integration by parts to calculate this integral. So in accordance with integration by parts, this is equal to u times v, which is f times e to the power of minus st, and I have to evaluate it from 0 to infinity. Just remember, when I put infinity in here, it's actually a limit, but for simplicity, I show it like this. Minus integral from 0 to infinity of u, which is f, times v prime, which is minus s, times e to the power of minus st dt. And now I can evaluate the first term. And one thing we know is that we had a condition for a function so that it can be transferable using Laplace transform. And that condition was the function must be piecewise continuous. And if you remember, in the definition of piecewise continuous, I said that the function should have finite limits. So that tells me that f has finite limit even at infinity, but e to the power of minus st, as t approaches infinity, this whole term approaches 0, so the multiplication of f times 0 will be 0. And then at t equals 0, f will be f at t equal to 0, and the second term is e to the power of 0, which is 1, minus, and in this integral, s is a constant because we are taking the integral with respect to the t, so we can factor out minus s, and now we have negative times negative, so it will be positive s times the integral from 0 to infinity of f e to the power of minus st dt. And if we just go back to definition of Laplace transform, f e to the power of minus st dt, integral from 0 to infinity. This was the Laplace transform of ft, or capital Fs. So let's come back here. So we have exactly the same expression in here. So this is the Laplace transform of function ft. So in conclusion, the Laplace transform of df dt, or f prime, is equal to fs, or capital Fs, which is the Laplace transform of function ft, minus the original function f at time equals 0. So this last property is exactly what we were looking for, because it enables us to convert a derivative of function to an expression in terms of its Laplace transform and its initial value. So if we use this property, we can convert a first order linear ODE to an algebraic equation, as I will show you in the next lecture.